Alright. Hey guys, today we're going to be doing a bit of an intro to statistics. It's going to be pretty dense, vocab heavy. We're going to learn a lot of math and vocab words. Your analyzing scientific data document in your modules goes over this pretty well, and it goes into it more in depth than we will on this video, so make sure you follow along with that because it goes into more of like how to calculate stuff and like things like that. I didn't know how to fit this like 10-page document to a 10 to 15 minute presentation, and we'll see if I can keep that short. So let's just kind of jump into it. So what is statistics? Well, it's a branch of mathematics that involves the collection, analysis, interpretation, and presentation of data. Basically, researchers do statistical analyses in order to summarize and examine their data, look into it, see what's going on. It's used in every field, from things like biology to sports. Pretty much anything could utilize statistics in some way, shape, or form. Psychology, medical stuff, etc. A statistic is a value that describes a characteristic of a sample of a population, by the way. So that's like what a single statistic is. So why is it important? Well, you can use it to come to conclusions about decisions in your life. If statistically it's unlikely that you're going to be in danger doing a thing, it might make sense for you to choose to go ahead with that activity. Like, I don't know, skydiving. I don't think it tends to be very dangerous, depending on where you go. But, I mean, you can use it to come to any kind of conclusion, from mild things to extreme things. Statistics helps you determine between reasonable and unreasonable claims and conclusions. A lot of people use statistics to come to conclusions that they favor. It's good to be able to avoid those biases to get to the truth of something, so you can interpret statistics on your own, instead of just listening to like Johnny Hottie or something on the radio being like, this study says that 5 people who drank wine didn't get cancer, so that means I won't get cancer if I drink wine. People quote studies like that all the time without really understanding what's going on. So if you can actually get into the meat of it and realize, hey, that's not necessarily a reasonable conclusion, it'll really help you avoid having silly conclusions. Alright, so there's 2 main types of data. There's quantitative, which is data that can be measured or counted, and it's gathered objectively. And then there's qualitative, which designates quality, plot twist, or describes a type or attribute. Of course, there's a lot of subtypes to the various things that we'll talk about in this presentation, so here we go with these. Quantitative data has 2 subtypes, so there's discrete and categorical. Quantitative data, those are distinct, mutually exclusive categories with no intermediates. You get that mostly from like counting and stuff. So like the number of male versus female salamanders in my cave, presence or absence of salamanders, stuff like that. It's just sort of like you count them. And then there's continuous, which is on like a numerical scale with an order to the values. You get it mostly by measuring. So stuff like pH could be like anything from like 7 to 14 to 1 or whatever. Temperature, height, it's on a continuous scale. And then there's qualitative data, which is a lot more subjective, such as like the greenness of a leaf or the coarseness of fur. But that kind of stuff is still important because it does tell you certain qualities about your data. Populations are pretty important in statistics. So a statistical population is a collection or set of similar objects, items, or events that is of interest of a question or experiment. So, for example, if you want to census a whole population, you'll get a parameter, a value that describes a characteristic or attribute for an entire population. Let's have American men aged 40 to 49 be our example statistical population. The age is a parameter, I believe, and as well as like the sex. But wow, that's a whole lot of men. and it's real expensive to collect data on all of those men. I mean, think about it. There's probably like a bajillion of them. I don't know. I don't know exact numbers. So instead of trying to collect data on all those men, which would be a statistical nightmare and a logistical nightmare and very expensive, take a sample of those men and use it to infer info about all of the men. But, oh no, you didn't take a good representative sample. Now you have sampling error, which is the difference between the value of a characteristic obtained from a subset of elements, like a sample statistic, and the actual but unknown value of a parameter from the entire population. That's kind of a dense way of saying it. So, for example, let's say in the actual population, 50% of American men aged 40 to 49 are balding, but you ended up with a sample that happened to just only have like 20% balding men. Well, that's not really representative of the population as a whole, so you've got some sampling error. To avoid it, we'll go over it in the next slide, but try having a bigger sample and try to avoid sampling bias, so favoritism when sampling. Let's say you were looking into the baldness of that population of men and you were only taking samples from like hairdressers, like those men at going to a hairdresser. That could affect the baldness levels, because obviously a bunch of the bald guys are probably not going to go to a hairdresser. Hopefully that all makes sense. A good sample is both accurate and precise. You can see that with the targets. First one is low accuracy, low precision. You can see high precision in B, so all the points are really close together, but they're not accurate because they're not hitting the bullseye. C, you'll see high accuracy but low precision, so the points aren't very close to each other, but they are all around that bullseye. So they're accurate, but they're not precise. And then D is high accuracy, high precision. You really want to hit that bullseye closely for a good sample, essentially. And you want a large sample. The bigger the sample, the better, because you're going to avoid a lot of variance, and you're aiming for it to be unbiased. All right, so two basic types of statistics: descriptive and inferential. So descriptive statistics allow scientists to organize, summarize, evaluate, and present data in informative ways. There's two main types, again. Measures of central tendency, which summarize a quantitative data set. It could be continuous or discrete, by identifying the central location or position of data values in the data set. So mean, dash average, median, mode, etc. Those are all measures of central tendency. And then measures of dispersion describe the variability of your data values within a sample. So range, variance, standard deviation, etc. Those are all measures of dispersion. All right, so the document goes more in depth on like calculation and stuff, but here are some basic vocab words for descriptive statistics. So the mean is the average of the data values, and you calculate it by summing all of the data values and then dividing the sum by the total number of the data values in the data set. Say you had like 1, 2, 3, 4, 5. Well, you would sum that up and then divide it by 5, because there's 5 values in that data set. Median is the middle value of a data set when they're ordered from lowest to highest. It divides the data set in two, and it's less affected by outliers and skewed data. Oh, by the way, means are useful when you have a normal distribution, so that's sort of when values closest to the mean are more frequent, and those furthest from the mean are less frequent. And then last but not least, mode. That's the most frequent data value in a data set. It is helpful when you want to know what value is the most common in the data. And then if no values are repeated, then you don't have a mode. Alright, so here's range, which describes the span of the data. Basically, it's the difference between the smallest and the largest data values in the data set. Then you have variance, which is like the almost mean of the squared deviation or variation between the mean and each data value. Variance and standard deviation provide insights into how much the data values will vary from the mean. The more variation you have in your data set, the more widely the data values are distributed from the mean. And then last but not least, standard deviation, which is also goes by capital S, capital D, or just lowercase s. And that quantifies the spread or variation of the data values in a sample, like sample variance, but in the same units as the mean and data values. Last but not least, you have standard error of the sample mean, also goes by capital S, capital E. I specify capital versus uncapitalized because you'll get different statistical things so like uppercase R might mean something completely different from lowercase r, so it's good to know. Anyways, so standard error of the sample mean is a measure of how accurate the mean of any given sample is compared to the true population mean. So a lot of this I just took right from the document. It's just sort of easier to just read it out instead of rewording it, because then you get everything you need. But anyways, so inferential statistics. We use inferential statistics to make inferences about a population from data derived from samples. We also use it to make decisions about whether observed differences between groups or treatments are true, or if they occur due to chance alone in whatever study you're doing. Specifically, these decisions tend to relate to the hypothesis or hypotheses being tested. So essentially, is the hypothesis supported, where you fail to reject the hypothesis, or is it not supported, where you reject the hypothesis? Scientists will make decisions about the hypothesis by determining the probability if there is a true effect, or if what they observed is due to chance alone. You'll hear about this a lot if you go into science and such. You'll hear about p-values. Everyone wants to use a dang p-value. They range from 0 to 1, and they assist in making these decisions. If a p-value is 0, then we determine it's impossible for the observed effect to be due to chance alone. If it's 1, it's due to chance alone. If the p-value is less than 0.5, that's usually the metric that people tend to accept. Some people use 0.1. It means that there's a less than 5% chance that what we see is just due to chance. Then you would reject the null hypothesis, and it supports your not null hypothesis, your experimental hypothesis, or whatever it was called. All right, here's some more vocabulary for inferential statistics. Here are some of the analyses that you run with inferential statistics. So, students' t-test used to determine whether there is a significant difference between the means of two groups or treatments by examining the variances around these means. And then you've got an ANOVA, which is kind of more, it's for more than just two groups. It's the party version of the student t-test. It will tell you if there is a significant difference between groups, but not which groups have a significant difference versus other ones. You'll have to use a post hoc test for that. It's not super important right now. Correlation is used to establish whether there is a relationship between two continuous variables by measuring their degree of association. It's typically linear, or correlation coefficient. That's denoted by lowercase r. Here's another one of these things where it's lowercase r, not uppercase. R ranges from -1 to 1. The closer that your value you get, your value of r for whatever study you're doing, is to these two extremes, the stronger the association is between your values. So -1 is a negative correlation, +1 is a positive, and then if you get around to 0, there's no correlation between your continuous variables. So correlation will tell the strength and the direction of the relationship, but not the nature of it, because correlation does not equal causation. That's definitely a concept that most people don't seem to get. Kind of like there's this one graph where it's sort of like the number of people who eat ice cream during the summer increases, and also murders increase during the summer. So if you think that correlation implies causation, well, ice cream causes murders. No, that's not how it works. So always keep in mind correlation does not equal causation, because a lot of other scenarios are going to be a lot less wacky. Then we have a regression analysis, determines the relationship between two continuous variables when there are clearly defined independent and dependent variables. It assumes that the values of one variable, the independent variable, are predictive of values in the other variable, which is the dependent variable. And this is like the stuff we did, what was it, like our first or second lab. A linear regression analysis assumes a linear relationship between the independent and dependent variable and fits a best line with, y equals mx plus b. M is the slope, b is the y-intercept. It's like you got in 8th grade math or whatever. And the strength of this relationship is measured by the coefficient of determination, R2, the correlation coefficient squared. So R2 ranges from 0 to 1. 0 to 1.0, with 1.0 indicating that the values of x perfectly predict y. And then there's a chi-squared test, or capital X squared. That's a contingency test for independence that determines whether a relationship exists between two categorical variables. A significant result indicates that the variables are not independent and thus they are related. Okay, that's basically that. Like I said, the document goes more in depth than I could in this short presentation, so please refer to it. Here's a salamander for getting through this. Yeah.